Hey everybody, so let's go ahead and try this one together. Okay, so an 85 kilogram skier is coasting down a 28 degree incline or 28 degree slope. Okay, her initial velocity near the top of the slope is 4.3 meters per second. She accelerates down the hill due to gravity, right, despite a kinetic frictional force of 97 newtons. So what we are asked to do here is to determine the skier's velocity after she has traveled 160 meters down the hill. Okay, so let's try this out. So there's actually two ways that we could do this, right? There's probably multiple routes beyond that we could do this, but I'm going to run through two different ways that we could solve this problem. And you'll see that we get the same answer basically, right? Despite whatever small rounding errors we might have, we basically get the same answer from both routes. And I actually personally find that really satisfying when that happens. So the first thing I'm going to go through is the kinematic method, where we just use the kinematic equations. And then I'm going to use the work energy theorem. And both will lead us to the same point. Okay. So the first thing that comes to mind is the following equation. Right? So excuse me, let me get my marker here. So V final, which is what we're actually being asked to calculate, the final velocity, right, squared, equals V naught, or the initial velocity, also squared, plus 2 times the acceleration times the displacement. Okay. So one of the nice things about this is we actually don't really even need to rearrange anything about this equation, right? It's already set up to solve for what we want. It's set up to solve for v, or rather v squared, but then we can just take the square root of this entire thing and it would solve for basically just v. And we have the displacement, right? We know that this person is moving 160 meters down this hill. Okay, we have the initial velocity, right? What we don't have just given directly in the problem is A. We don't have her acceleration. Okay, but we can find the acceleration, okay? Because if you remember, acceleration, as per Newton's second law, equals the sum of all the forces externally acting on an object divided by the mass of that object, right? We have the mass, right? The skier, right, combined with all of her gear and her clothing and everything, have a mass of 85 kilograms. Okay. So if we can find the net forces that are acting on this person, we can find the acceleration, and then we can just plug that in to the kinematic equation and solve for v squared, right? The square root of that would equal v. Okay. So the next question we need to ask ourselves then is, what are the net forces acting on this person? Okay. And what I want to do here is I want to add a representation of the x and the y axis. So let me get some lines in here actually. So let me try to get this where it needs to be. We'll put a y axis here, okay? And make that like a dashed line, okay? Now let me put in here, let me put in here another shape here, another line for our x-axis. Okay. You might notice that the x and the y-axis are a little bit tilted, right? They're tilted to sort of be center mass with the object, in this case, the person. Okay. we can do this, right? The X and the Y axes, they're not real, right? They're imaginary tools that we use to orient ourselves within a particular situation. And as long as we stay consistent about where they are and where everything else is in relationship to those axes, we can draw them wherever we want, okay? And sometimes it's convenient to sort of tilt them, right, in a way that's congruent with the tilt of an incline, or the angle of an incline, okay? And you'll see why in a second. So what I want to know, right, is if this is the x-axis, and let me label these, okay? Let's call this my positive x, okay? This downhill direction. Let me call this my negative x, okay? Let me call this my positive y. And let me call this my negative y. Okay. Her motion now is purely in the x-axis, right? Then what I really want to know, right, is what are the forces acting on this person in the x-axis, okay? So what we do know, what we absolutely know here, right, is that there is a kinetic frictional force, right, opposing her direction of motion. We know that her direction of motion is downhill, okay? And the direction that would oppose that would obviously be uphill, right? And let's call this our FK, or our kinetic frictional force, okay? So what we also have, right, is weight, right? We have her weight, and her weight is a product of the interaction between mass and gravity, okay? And it's going to create a forward force, right, that opposes the kinetic frictional force. And they're going to interact with each other, right? And they're going to sum with one another, and they're going to create some sort of net force that produces an acceleration as she moves down the hill. Now, the thing about the weight, right, is the weight points straight down. I probably could have gotten that straighter. Let me try that again. Okay. That's the best I'm going to do. So there is our weight, okay? What we can see here is this is offset, right? This is offset from our y-axis, right? And this sort of helps us rationalize the situation a little bit, right? Because if she were just sitting on the ground, right, 100% on a completely flat surface, if that were the case, 100% of her weight would be in the y-axis. But because she is now tilted 28 degrees, right, to be exact, part of her weight is in the x-axis and part of her weight is in the y-axis. And it's the part of her weight that's in the x-axis that's going to help move her forward. So what we need to do is we need to figure out what part of that weight has now been shifted into the x-axis, or the horizontal axis, okay? So what we see is that there's some degree of offset, right, between the y-axis and our force vector W, right? And that's going to help us find, so the degree of offset from that, right, is going to be a component of the part of W that's now in the x-axis. So let's think about this logically. If it took 28 degrees of elevation or deviation from the ground, right, to offset W this much from the y-axis, because if we're just flat on the ground, it would be 100% in the y-axis, right? But if it took 28 degrees to do that, to move it this much, then it must have also moved 28 degrees from the y-axis. So what we can say here is this is basically 28 degrees. It's exactly 28 degrees. Okay. So now how do we find the part of this vector that's in the x-axis? Well, let's see. The part of it that's in the y-axis, right, would be the part of it that's straight up and down, right? Okay. the part of it that's in the x-axis would be whatever component, whatever vector component of this, right, is horizontal. So what we're going to do is, this is a right triangle where this is the horizontal component and this is the vertical component, right? And this is sort of the hypotenuse of the whole thing. Then what we're going to do is we're just going to use whatever whatever trig function we need to find this horizontal component. That's going to be sine, right? Because this side of this right triangle is opposite to the 28 degree angle, okay? And remember what SOHCAHTOA tells us, that the sine of theta is equal to the opposite side of the right triangle divided by the hypotenuse. And so then if we want the opposite side, we just need to take the hypotenuse and multiply by the sine of theta, okay? So because this is opposite to this, we're going to take W basically, and we're going to multiply it by the sine of theta. So W in the X, right? So let's say, so W in the X is going to equal W times sine of 28 degrees, okay, which is going to equal 85 kilograms multiplied by 9.8 multiplied by the sine of 28. Let me just do that right now. So 85 times 9.8, okay, that's the weight, it's 833 newtons, multiplied by the sine of 28, gives us 391. .07 newtons, okay? So weight in the X equals 391.07 newtons, okay? Let me erase all this now. So knowing that, right, sum of all forces isn't that mysterious, right? Sum of all forces is just going to be, right, 391.07 in the positive direction, right, minus 97 newtons, right, since those newtons are facing in the x negative direction. Okay, so I'm just sake of completeness. Okay, so acceleration then equals 391.07 minus 97 divided by our 85 kilograms. Okay, and so then A equals 391.07 minus 97 divided by 85. Okay, so A equals 3 0.46 meters per second squared. Okay, so that's her acceleration as she moves down the hill for these 160 meters. Okay, so let's run this. Okay, let's just plug this in. So V then is going to equal square root of V naught squared, so 4.3 squared plus 2 times 3.46, okay, times 160 meters. Okay. And then V final, right, will equal, let me run it. See, 4.3 squared plus 2 times 3.46 times 160. Then the square root of that entire thing. Okay. So V final is then 33.55 meters per second. 33.55 meters per second. Right? Okay. So these forces interacted with one another, right? Only the x component of this weight, right, contributed to this person's acceleration, right, down the hill, right, with 97 newtons resisting it, okay? And with this kinematic equation, we can see we can very easily solve for what this person's final velocity is at any point in the journey, as long as we know what their displacement has been, right? And we don't even really need time in order to do this, right? Time could be included in here and then we would use a different approach. But let me go through this again now, right? But with the work energy theorem. And you'll find that there's a lot of similarities, a lot of actually overlap between these two approaches. There's a lot of relationship between the kinematic equations and work energy. So let me erase some of this, okay? And we'll see if we can get a similar answer. Okay. So work, the definition of work. And we're going to use another W here, but the W that I'm using from here on in is basically just work, okay? Definition of work is a force, right, applied to an object, right, multiplied by the cosine of theta, and theta being the deviation, the degrees of deviation between the force applied to the object and the direction of the object's displacement as a result of that force, okay? Multiplied by displacement. And displacement is often represented just generally with an S. I know we often, you see in basic physics problems, people will use a delta X or a delta Y. S is just a general way of expressing displacement without having to put it into a particular axis, right? But in this case, we're going to be talking about the displacement over the X, which is just 160 meters, okay? So what the work energy theorem basically says is that another definition for work is the change in kinetic energy. In other words, kinetic energy final minus kinetic energy initial. Okay. And if you remember what kinetic energy actually equals, right? Kinetic energy equals 1/2 the mass of an object multiplied by the velocity of that object squared. Right? So in other words, then the kinetic energy final for this person would be mass of the object, right? 1/2 the mass of the object multiplied by the final velocity of the object squared. Right? Okay. So we could actually use this to solve for the final velocity, couldn't we? Right? If we multiply both sides by 2, 2 cancels, okay, and then we end up with KE final, okay, equals m final velocity squared. And we could just divide m by both sides and take the square root of both sides. And we end up solving for VF. So VF, velocity final, ends up looking like this. Velocity final equals square root two times the kinetic energy, also final, divided by m. Okay. All right, fair enough. How does that help us though? Right? Because I don't actually know what the final kinetic energy is. Well, that may be true, but we actually know a lot about this situation, right? We know quite a bit. And let's solve, so if KEF final, right, or KE final, right, is the term that we need up here to really solve for the final velocity. Let's solve for what else KE final might equal. Okay, so if we look at this, right, we can very simply solve for the final kinetic energy in the work energy theorem, right, by just adding the initial kinetic energy to both sides. And so KE final also ends up equaling the initial kinetic energy plus work, right? Well, if this term right here equals this, then couldn't we just punch this into this? Yeah, we could. And then you might ask yourself, well, do we know work and the initial kinetic energy? And as a matter of fact, we do, right? Because this is the same as saying 1/2 mass initial velocity. It's an ugly knot I just drew. Okay, initial velocity squared. That's the initial kinetic energy, plus force times displacement. We know all of those things, right? The net forces, right, the sum of all forces, right, in the x, we just simply say the sum of all forces, which is going to be equal to the weight, the component of the weight in the x, right, minus 97 newtons, right, the force that opposes this. Okay, that's going to be F. Our S is just 160 meters, right, the displacement that the skier experiences downhill, okay? We know the mass, we know the initial velocity is 4.3 meters per second, right? So couldn't we just substitute all of this into the value for kinetic energy final, multiply it by 2, divide it by the mass, and take the square root of it, and then we'd have the final velocity, wouldn't we? So let me rewrite this now with that in mind. So final velocity then, okay, it's going to be equal to, once again, the square root of 2 times one half m v naught squared plus that was terrible. Okay, I apologize. Plus the sum of all forces, right, in the x-axis anyway, multiplied by s. And then all of that over m. And that is our equation. This is what is going to solve for final velocity for us. So let's plug some numbers into that and see if we can get the same answer that we got before, which I believe was 33.55 meters per second. It might come up a little bit different, right? It might come up by, different by, a hundredth of a meter per second. And that can have to do with rounding errors. That can tell you that maybe you're rounding a little bit too much or your calculator is rounding a little bit too much, but you get the idea. You wouldn't get that close just randomly, right? And there's a strong relationship between these two methods. So let's plug some actual values into this. Final velocity is going to equal square root of 2 times 1/2 the mass, which is 85 kilograms, multiplied by the initial velocity, which is 4.3 squared, plus the sum of all forces, which is going to be 391.07 minus 97. So leaves us with 294.07 newtons. 294.07 newtons. Okay. Times the displacement, which is going to be 160 meters. Okay. Divided by 85. Okay. Let me run this through on my calculator. I encourage you to follow along and do that as well. Okay, so 2 times 1/2 of 85, which is 42.5. Okay. 2 times 42.5 times 4.3 squared plus 294.07 times 160. And then divided by 85. Okay. And then the square root of that entire thing. And yes, not really any error at all, actually. What I came up with is 33.549, which I think it's fair to just round up just slightly to 33.55 meters per second. Okay. And there you have it. 2 different methods of finding the same answer. So it's really whatever you feel more comfortable with or whatever you're being asked, honestly. But the more you understand this kind of relationship, right, between the kinematic equations and the work energy theorem, the more you can really do with either one of them, right? For instance, you can start to not only measure how things move, but why they move, right? And start to draw conclusions about the force that made something move a particular distance, right, as ascertained by a kinematic equation. Right. So I hope this all made sense. And thank you. Thanks, as always, thanks for watching.